Hello everyone, my name is Panpan Zhao. I'm from the Institute of Information Engineering and the University of Chinese Academy of Science. Today, I will present a paper called TMT-RF, Tunnel Mixed Traffic Classification based on Random Forest. I will briefly introduce this paper from the following 6 aspects. First, I will introduce the background of this paper. Tunnel is a kind of encapsulation technology. The technology uses a network protocol to encapsulate data messages generated by other protocols. The new header provides routing information so that the encapsulated data can be transmitted over the internet. The working process of the tunnel is shown in Figure 1. First, the packet is encapsulated by the tunnel start node and then transmitted in the network. Finally, reaches the tunnel end node for decapsulation and reaches the destination. In recent years, tunnel traffic analysis has received more and more attention, mainly for 4 reasons. The first is the increased demand for tunnels. During the prevention and control of the new chronic pneumonia epidemic, tunnel technology has become one of the main technology means for remote office personnel to access the unit network. The second is the growth of malicious traffic. Tunnel traffic weakens the efficiency of defense in defense. 70% of malicious service bypass firewalls and intrusion detection systems through tunnels and encryption technologies. Then there are many difficulties. After the tunnel traffic is encapsulated and encrypted, the characters of the orange traffic have undergone major changes. Compared with encrypted traffic, the identification of tunnel traffic becomes more difficult. Finally, the equipment lacks support. Traditional network equipment lacks support for tunnel traffic identification, which poses a high security risk. The traffic in the tunnel is mixed. The scenario of a single user using the tunnel is shown in Figure 3. The user in the tunnel may use lots of applications within a period of time. Tunnel traffic has the same sender and receiver, so it is difficult to use clear text information such as IP. The traffic in the tunnel is mixed, and there are 3 types of mixed traffic in the tunnel: positive time separated application traffic and zero time separated application traffic, negative time separated application traffic. The existing traffic classification method cannot be used for tunnel traffic classification. To solve this problem, we propose a framework based on split called TMT-RF. We found that the tunnel traffic mix is complex and diverse. We segment the mixed traffic firstly, and then extract figures for classification. As shown in the Figure 5, the TMT-RF include 3 paths. Noisy split model. The second model is the combine burst and feature extraction and classifier model. The noisy split model is to split the tunnel mixed traffic for the first time. It mainly includes 3 paths: based packet splitting, based classification splitting, and splitting decision. There are continuous noisy data packets in the middle of 2 positive time separation applications. The mixed flow can be split through the noisy data between positive time separation applications. The classifier recognizes the noisy data packet, and if it is noisy, then split. After splitting, there will be a variety of results. For example, split success and split failure. We need to choose different modules for different results. The effect of splitting is measured by splitting accuracy. If the predicted split point is within the allowable error range of the true split point, the split is correct. Once we have used noisy split for the first split, we can use the combine burst model for a second split. This model mainly deals with overlapping mixed traffic. It mainly includes 2 paths. The first part is burst splitting, and the 2 paths is burst combine. The first part divides the mixed stream into bursts. The mixed flow can be divided into a lot of bursts. The second part merges bursts to improve classification accuracy and reduce time delay. After 2 splits, we obtained the traffic of a single application. Now, the existing traffic classification method can be used for classification. The processing of this model includes 2 processes: the processing of the results of the first split and the processing of the results of the second split. In traffic analysis, 3 types of features are usually used. They are packet size, time interval, and packet direction. In our methods, we use the packet length and packet direction. We use the random forest classifier that is often used in traffic classification papers. After the secondary division results are classified, the final classification results must be obtained through majority voting. In order to evaluate the method, we propose a framework to generate tunnel mixed traffic. Firstly, we collect the encrypted application traffic and then replay the encrypted application traffic to the tunnel. As shown in the figure 10, the framework includes the 2 paths: application traffic collection model and tunnel playback model. Application traffic collection model is to collect encrypted application traffic. Firstly, using the black domain software to turn off irrelevant applications. using TCM dump to capture application traffic. Next, using ADB Monkey to simulate user usage and generate real traffic. Finally, we generated 30 application traffic of 7 types. After the encrypted traffic is collected, the tunnel mixed traffic is generated through the tunnel playback model. Firstly, a tunnel is established between host A and host B. Host A as a client, host B as the server. Host A reduces the data packets in the C2S direction in order, and sends them to host B through the tunnel. Next, host B reduces the pickup field in order, and when it receives the previous data packet in the C2S direction, it sends data packets in the SOC to host A. Next, repeat the above operation. Environment required for data collection as follows: 3 computers, mobile phone, Python, Skype, et al. Data collected from August to October. Positive time and zero time separation application traffic collection includes 6 classes, and each class includes 100 instances. The application flow of negative time separation includes 2 types of 5% and 10% overlap rate. We evaluate the impact of packet length series, measure range, and the number of combined bursts. As shown in the figure 6, TMT-RF can achieve higher split accuracy when packet length threshold is 125. As shown in the figure 7, TMT-RF can achieve higher prediction accuracy when measure range is greater than 6. As shown in the figure 8 and figure 9, the number of combined bursts should choose 10. As we can see from the figure 10 and 11, our TMT-RF is closer to the classification result under the single application assumption. The classification results of the second application is most affected by the mixed flow. As shown in Table 1, the overlap rate and output probability threshold have a greater impact on the classification results. As we can see from the table, our TMT-RF outperforms other methods on all datasets. On zero-time separation application, since this task is easy, all the methods achieve high performance. In the negative time separation application classification tasks, there is a mixture of traffic under different overlap rates. We can see that the stagnation recall is relatively low, mainly because of its equal sharing idea, which is very unfriendly to mix the data of long and short streams. Okay, to conclude, in this work, we propose a novel method named TMT-RF for tunnel mixed traffic classification. We introduced the two-partition architecture of mixed streams. We collect 4 datasets in 3 different granulate to evaluate our model. Results show that TMT-RF outperforms other methods on all datasets. In future, we need to study the use of loss of people in the tunnel. That's all. Thanks for your listening.